Okay, so we'll start again here. I did want to do some practice problems, so I've got a few of these written down, and so we'll try and work through these. I did one video for practice problems this afternoon, so I will get that one posted here as well. All right, so here we have a nitric acid and calcium hydroxide. So you have an acid and a base. So theoretically, we have an acid-base equation where if you're doing acid-base chemistry, right? If you recognize that it's an acid and base, okay, so this is kind of where we left off last time. If we recognize that the problem is acid and base, we potentially can use this equation, okay? In this particular case, where the problem is starting off with, you have 4.85 grams of the calcium hydroxide, right? So, and then it wants to know how many grams of the HNO3 are we, how many grams of HNO3 are we going to have if we have this much calcium hydroxide? So a lot of the acid-base problems are reactant kind of problems. Okay, so when we're doing these kinds of things, okay. Right. Oh, B. All right. So in this case, this first example, we're going from mass of A to simply what is mass of B in this case. So it doesn't matter that A and B are both reactants. Okay. So starting from the mass of A, which this part here was given, the molecular weights probably are. Let me put it this way. I will try to give the molecular weights on the problem when I give the problems. But again, it's going to be all on the computer. So theoretically you can, do a quick calculation on those as well. But again, we should be able to calculate the molecular weights. That shouldn't be the focus of the problem. So given the 4.85 grams of the calcium hydroxide, right, our first step is the molecular weight. Okay, that gives us step one. The balanced equation is going to be step two, and then the molecular weight rounds out step three, okay? And so that's what you're going to see here in this problem is the molecular weight, the balanced equation, and the molecular weight as the steps, okay? And so here we have the 70.096 grams per mole for the calcium hydroxide. For every 1 mole of the calcium, there's 2 moles of the nitric acid, and then nitric acid's molecular weight, 63. So we're going to multiply all the numbers on the top, divide by all the numbers on the bottom, and get a mass here of the nitric acid. Okay. Now, more realistically, what we have is this problem. Okay. Here's the same problem. It's just here we're told we have 12 molar HNO3 and we have 2.25 molar calcium hydroxide, which we have 350 milliliters of, okay? So we have the volume, we have the molarity, the second one, we just don't have the volume. So this goes back to, in this setup here, okay? Now we have the molarity is what we would need to be given, okay? So our step 1 is going to involve the molarity, then the balanced equation is step 2, and then the molarity is going to be in step 3. And so that's what you're going to see in this problem here, okay? So we have the molarity. Okay, so we're starting from the volume. So the volume here was 350 milliliters. You do have to convert this over to liters. So when we're doing the long method, you do have to convert this to liters because we want the liter units to cancel out here. Okay, so when we're using the M1V1 equals M2V2 or MAVA equals MBVB, it doesn't matter in that shorthand equation, but if we're doing out the stoichiometry, you need to move this to liters. Okay, so I start from the liters. Okay, again, that flow chart is what you want to pay attention to. That's going to help you to pick where is my starting spot and where is my ending spot, and then what steps do I have to take along the way to get from A to B. Okay, so here we have the molarity, which we were given. Okay, the 2.25 is a given value. All right, the balanced equation, again, okay, we have the balanced equation. You always want to make sure that you check your equations are balanced before you start using them. Again, you don't want to get through most of the problem and only to realize later that it wasn't fully balanced, okay? And then the last step is the molarity for the nitric acid, okay? And so here I'm dividing. And so this is how we get the MAVA equals MBVB equation, is because you got the volume, the molarity, the volume, and molarity, and so it becomes a multiply and divide kind of step. The only difference here is, even though recognizing that it's acid base, there is a slight adjustment to the acid base problem. Okay, so I gave you this equation. I gave you this generic equation before, all right? MAVA equals MBVB, okay? If we want this to apply to any acids and bases, you need to put this little adjustment factor on the ends, okay? You have to multiply the acid side by the number of protons in the acid. You need to multiply the base side by the number of hydroxides in the base, okay? Because if you have 12 molar sulfuric acid, okay, just like right here, you're going to see some different stoichiometry. It's not going to be 1-to-1, and so this is going to throw off your problem if you just plug in the molar volume into this equation, right? It's not going to work directly, right? This works fine if you have right? You have one proton, right? And one hydroxide. Okay, it works fine if that's your setup. Okay, you don't have to do the stoichiometry. Okay, but there's a couple of things that if we're going to use shortcut methods, we have to recognize when we're using shortcut methods or when it's appropriate to use them, and if there are adjustments required when we use those equations. Okay, so the generic equation here, MAVA equals MBVB, works fine with monoprotic acids and single hydroxide bases. Okay, but that's not always what you're going to see. So if you throw this little adjustment in here, okay, and then we retry that with our problem here. So if we try this with our problem up here, so I have 2.25 molar times 350 milliliter, right? That's my base, right? So my base side, and then right? So I don't know the volume of the acid, okay? This is the single proton, okay? This is the OH minus on the calcium, okay? So now when you do 350 times this, you're functionally getting this times this times this, right? Divided by 12, and then divided by 12, you'll get, the value will come out in milliliters, okay? So you'll get 131 milliliters when you do it that way, okay? So the stoichiometry won't lead you wrong. It's safe to do it this way every time. It's fine. But if we recognize when and how to apply our shortcut equation, then you can apply this. Okay. All right. So here's my other. Let's see. Does it look as blurry to you as it does to me? Yeah. Okay. That's not good. All right. Let's see if it resumes here. I don't know why that looks so bad. That is just terrible. Well, it's kind of an experimentation here. You know, they sent out the video on. Yeah, no, it's. You know, they sent out some whole thing on how to do this today, and was like, oh, here, try this out. This way you can do practice problems. And I'm like, all right, well, it's all right. So here, essentially, you've got a sulfuric acid and a potassium hydroxide, right? Again, the water and the salt are the products of an acid-base reaction, right? We have two molarities, we have a volume, and we're missing a molarity. So again, here, we're looking for the volume, right? We would start from the volume here, molarity, balanced equation, molarity, right? But if we recognize that it is an acid-base problem, then you can just use the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And the only adjustment here is the number 2, which comes from the 2 in the acid. And there's a single hydroxide. Okay. So you end up with the same answer. Okay. So you can do this kind of thing if we recognize that it's an acid-base problem. Okay. All right, let's look at a different kind of problem here. This is like perfect Murphy's Law, these kinds of problems. Is like, it worked perfectly when I was doing this stuff by myself earlier. I didn't have any problems with it. It's only when I'm doing this live that it starts to generate problems. All right, so this kind of problem here looks back to determining whether or not something is an electrolyte or not. Okay, so we looked at some of the stoichiometry stuff. Again, I will continue to post other practice problem videos as I do them. You can take a look at the first one, then we'll see how the first video plays out with doing some of the practice problems. I'd like to make other more individual practice problem types of videos, so that way when you're looking for a, how do I do this kind of practice problem, that you don't have to wait, or wade through like an hour and a half video in order to find the practice problem you're looking for. So in this particular problem here, we're looking at obviously salts or maybe not salts. And so the question is it an electrolyte or is it not an electrolyte? Okay, so we don't know anything about necessarily the solubility. You don't necessarily need to apply solubility rules. In these kinds of problems, it's looking for more, can you recognize an organic compound versus an inorganic compound? Okay, so anything that's inorganic in these kinds of problems, we're functionally going to be looking for the metal, non-metal, inorganic salts. Okay, it doesn't really matter whether or not, like cesium, is super, dissolves really well or not. Doesn't really matter much about the calcium nitrate, but simply just that recognizing that this is an ionic compound and that this is an ionic compound, that they are both electrolytes. Okay, so remember our definition for electrolyte was that it makes ions in solution, which then become electrically conductive. Okay, so we are conducting electricity through the production of ions. So this one would be a tricky one. Okay, anybody know what the name of this compound is? Good. Remember, we didn't really have this in our nomenclature. So this is methanol. Okay, this is methanol. All right. So even though it has the hydroxide in there, okay, it really falls into the organic nomenclature. Okay, and so the hydroxides actually are considered our alcohols in organic molecules. And then over here we have sugar, right? The C6H12O6. So sugars are organic, so they again are not going to produce ions in solution, and so they are non-electrolytes. They still dissolve in water, but they're but they don't produce ions. Okay. Same kind of thing here with these other problems. We have magnesium bromide, so a metal, non-metal ionic compound. Sodium carbonate, a metal, non-metal ionic compound. Potassium and hydroxide, a metal, non-metal ionic compound. And then some other larger sugar molecule. Okay, so in these problems, simply finding that they are ionic is all you really need to be doing in order to identify that it is an electrolyte. Okay. Now, the harder ones, okay, so this would be a slightly harder problem, okay, is determining whether or not it's soluble or not. Okay, so again, this is another good example of a kind of test question that we may have to deal with as far as solubility. So determining if it's an electrolyte, okay, good test kind of question. Again, multiple choice, it's easy to put these kinds of things in there as a multiple choice question. Which one is an electrolyte? Which one is not an electrolyte? Or, you know, if it's, you know, click all the ones that are electrolytes and, you know, and have that be the answer. I'm sure there's a multi-answer option where you could pick that, or count how many are electrolytes out of a group, or how many are non-electrolytes out of a group, okay? So there's a bunch of variations on that first problem of looking at just simply electrolytes, okay? This next problem, as we get into the salt kind of questions, again, could just be, what happens when I put this salt in water? Is it soluble or is it not soluble? Okay, and so it comes down to how readily do you understand those solubility rules? How much do we have them? Well, probably not memorized, but for the most part, how readily accessible is it, you know, in your memory and or, you know, notes that you have on hand to come up with, you know, what is, you know, whether or not it's soluble or not. Okay, so silver nitrate. Okay, so this is where knowing our rule number 1 ions, okay, that small group, that one slide that has a bunch of stuff, the rule number 1 ions, things like nitrate, acetate, nitrate, and ammonium are all rule number 1 ions. So these are all going to be soluble then, simply because they contain those ions. It doesn't matter about the lead. It doesn't matter about the silver or the sulfur, okay? The potassium and the nitrate are both rule number 1 ions. So just identifying which ones have those ions, we know those salts are going to be soluble, okay? Right? As we move down to things like this, so we have silver iodide, copper phosphate, cobalt carbonate, and potassium phosphate. Determining whether or not they are soluble or not, okay, again, goes back to your solubility rules. The iodine is in the group with the halogens, chlorine and bromine, that are generally soluble, except when they are paired with silver, mercury, and lead. So paired with silver here makes this a insoluble compound, okay? Our phosphates were generally insoluble. So there wasn't a rule for copper here, but the phosphates were generally insoluble. And so that means unless their only exceptions were things like the rule number 1 ions, okay? Again, the carbonates, generally insoluble. So it didn't really matter what they're paired with unless it's one of those rule number 1 ions, okay? Phosphates, again, were generally insoluble, except when paired with a rule number 1 ion, of which potassium is one of our rule number 1 ions. So this one becomes soluble because of the potassium, okay? All right, so let's look at another solubility question here. Okay, so here we have a chromium 2 bromide and sodium carbonate, okay? If we're gonna, so this would be a fairly realistic test question. The question is, what is the molecular equation? Okay, writing the molecular equation is writing the products with their proper designations. Okay, what are the products here, right? So, okay, keeping in mind that the positive ions are essentially swapping partners, okay? The oxidation state on the chromium is +2. So whatever it makes on the other side, it is still going to be +2. That's the key thing here, is that these don't change the oxidation state. The charge doesn't change in these problems. All right. So you've got okay. Now these are all aqueous to start with, right? So the question is, what happens after they mix? Okay, what is the result of their mixing? Okay, sodium, rule number 1 ion, right? So that's always going to be aqueous. Carbonates were generally insoluble, except with the rule number 1 ions, which chromium isn't. So this is going to be a solid. Okay. And then you'd have to balance it, right? That's the other step here is balancing, right? So we'd have to put a 2 there, right? So the balancing equations, so I can post, I think I forgot to do that, but I have some balancing equation practice sheets that I can post up and you guys can work on. So by putting the 2 here, it multiplies everything by 2. So that gives me 2 sodiums, and then that matches the 2 bromines. Okay. All right. So this would be the molecular equation. Okay. So our second kind of problem that we might have from a problem like this is, what is the total ionic equation? Okay, so our total ionic equation is we separate anything that's aqueous. Okay. Okay, so solids, liquids, and gases don't get separated. Okay, so this is a good spot where if you have a multiple choice problem where you have 5 choices of total ionic equations, where you might see some variability and or wrong potential choices, is giving you the wrong charge to start with here, because again, you should be able to pick out what the charge is, but obviously we have to check that it's all written right, right? If we're splitting it into its ions, we should functionally know what its ions are, okay? So if it separates into the wrong ion, right? So this shouldn't separate into like, you know, CO2 and an oxygen or something like that, again, because you'd have to recognize these are polyatomic ions, right? So this becomes this, right? So out of this problem then, our next step could be, what are the spectator ions? Okay, the things that haven't changed. So the sodium is a rule number 1 ion. The rule number 1 ions, I said this in last time, rule number 1 ions are always spectator ions if they are present in these reactions, because they're not soluble. We're looking for the production of insoluble compounds. So if we already know it's not going to be insoluble, then it has to be a spectator. Okay. The bromine, by not changing, means that, you know, it's bromide over here and bromide over here. Okay, nothing has changed with it. Okay, but the chromium is not just a chromium 2 plus over here, right? It's not just carbonate, it's a molecule over here, so something has changed. Okay, so identifying our spectator ions might be another question. Okay, that's 3 different questions here out of this one problem. All right. The last one, though, we have one more that we can do from this. Okay, is writing the net ionic equation. Okay, so if you eliminate out the spectator ions, the question is what's left? Okay, I eliminate everything else, take out the spectator ions, and what you have left is the net ionic equation. Okay. Let's do one more of these, but let's do my super hard one. Okay. All right, I guess I'll just keep going with this one here. All right, so here is what I usually give. Now, obviously this one is harder to do if we're doing this in person, right? If we're doing this on, if we were doing this one in class, all right? So you have all right. So imagine doing this one in class or on a test, okay, where I don't give you the molecule. You have to remember your nomenclature stuff, okay? Like I said, you can see these kinds of things in homework problems, okay? So we have ammonium sulfate and strontium chloride. Now we want to know, what is the molecular equation? Okay, what would be the molecular equation? Okay, what is the molecular equation? So we have to first write down what are these molecules. Okay, so ammonium, right, and sulfate, right, and so our drop and drag making molecule, we have strontium, right? Strontium is in the same family as barium, so okay, and then these are going to swap partners. Okay. The question is then, what happens once these swap? Okay. So in this case, the sulfates were generally soluble, except strontium is one of the exceptions. All right, so it ends up being a solid. Ammonium is one of our rule number 1 ions. All right, so it's aqueous. All right. You could separate out and do the total ionic equation. Everything that's aqueous gets separated. You'd also have to balance that too. So that's just don't forget that. I don't really balance the net ionic equations, or I mean the total ionic equations, because it's a lot of ions to just be balancing. Okay. So the ions that haven't changed then are spectator ions. And then our net ionic equation, eliminate, take out the spectator ions, whatever's left over is your net ionic equation. Okay, it's your net ionic equation. I have a few more that I'll do the short videos on them, on doing a few more of these stoichiometry problems, as well as a few more of these kinds of problems. So that way, like, you have this video, plus you'll have some other shorter videos that go through these kinds of things as well for this chapter. Again, the next test is all on this chapter, so there's nothing else to do but this stuff for this next test. Okay, so it's just a matter of practicing. What we can probably do is, again, it's just a matter of like me getting the assignments put together. I could do like a practice homework one instead, and then that way you could kind of get an idea of like how well you're doing, like how prepared you are for the next test. Maybe if we do a kind of a practice homework type of thing, so I could replace one of those lab grades as well, because again, we still have 2 more lab grades that I gotta try and replace here too. So we could do some practice homework problems or something like that I could put together then as kind of like a study guide. And then that way, if you do well, then you would essentially know that you're prepared for what you need to do for the test. And then if you miss some stuff, then you'll know kind of more about where you need to focus your studies. All right. All right, let's take an early break here for 5 minutes, because I'm going to swap us over to the PowerPoint, because we do have one section left. I also want to take a look at the calendar again to see kind of where we're at. All right, so let's get back to calendar. Okay, so obviously we're here on the 1st. Still planning the 13th for the exam. Journal article, still due this Friday. The makeup lab assignment is due next Friday. Bibliography the Friday after that. All right. And so we've got basically a month left, right? So we have 2 more chapters to do after this. Okay. So, I mean, that's plenty of lecture time, to be honest with you. There's more than enough lecture time in here to do the other chapters, even at the pace that we're going. All right. So one of the chapters is relatively short. It's shorter. And then the other chapters, a regular chapter. So, all right. So we're getting close. We're still planning on the 13th for the exam. I'll probably do the exam the same way as last time, where it'll be those 2 days that you have to take the exam. But there probably will not be a take-home portion for the next exam. So it'll just be the points for the next exam. Okay, so it should all be on Canvas for the next one, since most of this stuff there's no pictures involved, so it's a little easier for me to put that into Canvas, I think. Okay, so we're going to finish up the rest of the chapter here. There's one segment left to do. Okay. Okay. All right, so let's take a look at where we left off last night. All right, so we went through the precipitation reactions. Okay, so I did a sample problem on this. I'll do another video that has the sample problems of this as well. We looked at acid-base reaction. So again, most of this stuff in calculating molarity changes is going to fall into the stoichiometry kinds of problems. So there's really nothing. There wasn't really much new there. The method is still going to be the same, but identifying acid-base reactions is going to be something that things like where we left off, the thing that you should know. Back to this slide here. Okay, the strong acids. Okay, you should know the strong acids. All right, you should know the strong acids because these are the only ones. Everything else other than these is considered a weak acid. Okay, so this comes back around in 112. So knowing these kinds of things now is good. It's good to know now. It helps for both now for this test and for future stuff. Okay. All right, so we talked about like the different kinds of acids, the acid-base stoichiometry that really falls into the same kind of stuff. And some of the titration. What I'll probably do is I will do a particular sample problem on titration stuff. I have a titration lab, so this is again could be a lab that we could do. But I'll do a practice problem for the titration stuff. Again, it's pretty much the same kind of stoichiometry problem I just did. It's just it's worded, of things like the acid and base are neutralizing one another, and what is the concentration of the acid, that kind of stuff. So it's similar to the rest of the stoichiometry stuff, but there's a slight variation on it. Okay. All right, so this is really our last segment, okay, is oxidation reduction, okay? So this stuff here, okay, so what I want you to be able to do are to determine oxidation states of any atom and a molecule. Now, this first one should sound familiar. This is pretty much what I had you do on the nomenclature quiz. So if you remember the nomenclature quiz, the stuff at the very bottom was determining those oxidation states. That's what this is. So if you got those parts right on the nomenclature quiz, then you should be fine in this first step, because oxidation reduction is about exchange of electrons. So you have to know what the electron state is to start with in order to determine whether or not it's changed, or we have to determine what it is beginning and end in order to determine how it's changed. Okay, so we want to be able to identify the changes, identify oxidation and reduction. Again, these terms will come, we'll get to them in just a second. Be able to identify oxidizing and reducing agents in a reaction. So a lot of this stuff is just identifying. You don't really have to calculate anything. So this is identifying the parts of this reaction. What's going on in a reaction, okay? All right, so we've talked about oxidation numbers, okay? For lots of compounds that are ionic, their oxidation states are their charges, okay? But we also know that things like carbon dioxide have oxidation states even though they're not ions. Okay, so the oxidation state was kind of the umbrella term. Everything has an oxidation state, but not everything has the charge. Okay, so ionic compounds have the charge. All molecules have an oxidation state, which is dealing with their electrons. Okay, what is the state of their electrons? Okay. There's some general rules that come into play here. So this is more dealing with our covalent molecules, okay? So obviously ionic compounds are relatively easy. We know the states, the oxidation states of things like the alkali metals, the alkali earth metals, those are +1 and +2, okay? We know things like oxygen's -2, the halogens are generally -1, again, by themselves, they're generally -1. Nitrogen family is generally -3. So we have some general ideas of what the oxidation state / charge is for ionic compounds. We don't always know this for if we're looking at fluorine. The element fluorine is F2, or carbon dioxide, or methane. How do we assign oxidation states to these organic molecules, okay, or to covalent molecules, all right? So a neutral element that is not part of a compound has a 0 oxidation state. So if we're talking about fluorine, the element, fluorine, F2, its oxidation state is 0, okay? Aluminum, solid, okay? Aluminum as a solid metal in its natural state as a metal, its oxidation state is 0, okay? In a molecule, aluminum has a +3 charge, but all by itself, as a metal, it's 0, okay? Sodium, the metal sodium, has a 0 oxidation state. Sodium ion has a +1, okay? So it can, in its natural state, it's a 0 oxidation state, okay? Monoatomic ions equals their charges. Again, the charges, their oxidation state is the same as their charge. They're virtually synonymous, okay? The sum of the oxidation states equal the overall charge of the formula. So this is kind of like the ones that I did in class where I would have said, okay, well, the total molecule was 0, so I put equals 0, and then what are the oxidation states of the individual atoms adding up to the 0, okay? Again, some guidelines that'll be helpful here. Oxidants, again, still tend to be -2. Hydrogens are going to be +1. Okay, so if we look at what are the oxidation states of these elements, okay, magnesium. Okay, it's the element magnesium. It's all by itself. It's not in a molecule. Its oxidation state is 0. Okay, phosphide. Okay, it has a -3 charge, which is equal to its oxidation state. Okay, iron in FeCl3. So this is just like the practice or the problem on the nomenclature quiz, right? There was like ruthenium hydroxide on the nomenclature quiz, and it was 3 hydroxides, and so you had to say, okay, well, the ruthenium on the nomenclature quiz was +3 because it was paired against 3 hydroxides. Okay, so just identifying what the oxidation states are, the first step. Okay, so this is similar. Okay, here's our potassium phosphate. Okay, what is this? What is the oxidation state of the phosphorus in this molecule? Again, straight off our nomenclature kind of quiz. All right, straight off our nomenclature quiz here. Okay, the overall molecule is 0. Okay, potassiums are all +1. They're alkali metals. We don't know what the phosphorus is, but we do know that the sum of the charges has to add up to 0, and oxygen is going to be -2, but there's 4 of them. Okay, so this is pretty much how I would have set it up when we were doing this before. There's 3 of the potassiums, okay, and so you get, so you basically have to group everything together. You get your -8, your +3, okay. All right, so that's right. So then, so here it's collecting terms. You see they'll put the -8 over here, it becomes +8. The +3 brought over becomes -3. So the oxidation state of the phosphorus is +5. Okay. So this is the first of 3 kinds of questions. So again, those same kind of nomenclature questions you're likely to see again on the next test. Okay, so oxidation reduction deals with a change in that oxidation state. What happens if the oxidation state changes? Okay, we want to be able to identify what's happening when it changes. Okay, so oxidation is a gain of electrons. Okay, or I mean, oxidation is a loss of electrons, right? So its oxidation state is going up, is increasing. Okay, reduction is when it decreases, so it's a gain of electrons. So there's a couple different ways that you can see this one. All right. So oxidation is loss of electrons. Reduction is gain of electrons. All right. So there's a couple of, let's see if where's my little mnemonics that. I don't have the little. Usually there's some little mnemonic ways of memorizing these. Okay. So there's a couple. Here, I'll write them down here. Okay, Leo says GR. Okay, loss of electrons is oxidation. Gain of electrons is reduction. Okay, so Leo says GR. So usually, like the the little graphic is like a little lion, and he's got the GR above his head. So it's kind of like a little way to memorize like what's going on for oxidation and reduction. The other one is oil rig. Okay, so oxidation is loss of electrons. Reduction is gain. Okay, so those are kind of two ways that people memorize what is going on for oxidation and reduction. Okay. All right. So here we look at a potential problem. Okay. So we have aluminum. Aluminum is a solid, so it's an element. It has a zero oxidation state. Chlorine is the element chlorine, has a zero oxidation state. Once it makes a molecule, then the aluminum becomes +3 and the chloride is -1. Okay, so the chloride then went from a 0 to a -1. It gained electrons, therefore undergoes reduction. Aluminum lost electrons and therefore undergoes oxidation. Okay, again, we're talking about negatives, so as it loses electrons, it becomes more positive. Okay, as it gains electrons, it's going to become more negative. Okay, so just identifying, so the question here is identifying what species is undergoing oxidation. Okay, that would be the question on the test. What species is undergoing oxidation? So if we're looking for what's undergoing oxidation, your choice is really, they're going to have to be reactants. Okay, they have to be reactants, right? What's undergoing oxidation? It's either going to be aluminum or chloride. Okay, so obviously in this problem, it's only two choices. Okay. All right, so let's look at two more examples here. So there's one other thing of nomenclature that we got to get to here, which is the agent part. Okay, so we have hydrogen and oxygen making water. Okay, hydrogen and oxygen are both elements, so they start out as 0 oxidation state. The oxygen in the water is -2. Hydrogen is always +1. So hydrogen is losing electrons and undergoing oxidation. Oxygen is gaining electrons and undergoing reduction. Okay, so another thing here that helps, okay, the original terminology for oxidation was that they thought it had to include oxygen. Okay, so if we go back here to this problem, okay, there is no oxygen here. Okay, so originally when they were coming up with these terms, they thought oxygen was the key thing. So that's how it got its name, oxidation. They thought it was gaining oxygen. Okay, iron was rusting because it was gaining oxygen. It was undergoing oxidation. Okay, that's what rusting is oxidation. So, but in this example here, with the aluminum and the chloride, you still have oxidation and reduction, but you don't have any oxygen. Okay, so when we look at these kinds of problems, okay, something to remember, okay, oxygen does not undergo oxidation. Okay, obviously, because in the original terminology as well, it would say it's gaining oxygen, but oxygen can't gain other oxygen. Okay, so oxygen is not going to gain oxygen and become like a super oxygen. Okay, so if you're looking for which one is undergoing oxidation, oxygen is not a good choice to pick for undergoing oxidation. Okay. We can also see here the hydrogen here is gaining an oxygen. Okay, it's gaining an oxygen. All right, it doesn't have an oxygen attached to him here, but he does have an oxygen attached to him here. The hydrogen is undergoing oxidation. Okay, so there's a couple different ways that you could look at this problem. All right, let's look at this problem. This one's a little trickier. Okay. All right, so first things first, what do we recognize on this page? What's something that jumps out at you? Okay, probably the 2 1/4, right? 2 1/4 charge or oxidation state, right? So this goes back to some earlier conversations that we had about this, was that oxidation states can be fractions. Okay, it's not a charge, it's an oxidation state. So when you have a charged species like sodium chloride, it loses a whole electron and becomes sodium, or the sodium ion. Okay, it can't lose half of an electron. So you can't have half charges, but we can have half oxidation states, or in this case, quarter oxidation states, because it's talking about sharing electrons, how evenly they're shared, and they can be unevenly shared around a molecule. Okay, so you don't have to have full oxidation numbers. It's also not really important for this problem either. Doesn't really matter. Okay, so if we look at oxygen, the element, gaining into carbon dioxide, again, the oxygen's the same in both of these, so it doesn't matter which one you would have picked, right? Because the oxygen here is -2, and the oxygen over here is -2, okay? Point is, it goes from 0 to -2. The carbon goes from a -2 something, right, to a +4, okay? For sure, it becomes +4. So the hydrogens here don't change their oxidation state. The only time hydrogen is going to change its oxidation state if it was like this previous problem here, okay, where it is hydrogen, the element, becoming hydrogen, the molecule. Okay, so hydrogen here is +1, hydrogen here is +1. There's no change in the hydrogen. All right, so there's only going to be two things changing. Okay, somebody's gaining electrons, someone's losing electrons. Okay, so oxygen is gaining electrons, undergoing reduction. The carbon is losing electrons and undergoing oxidation. Okay, so you just have to be able to pick out what species is changing, okay, and how is it changing? What is happening to the carbon? What is happening to the oxygen? Okay, you just have to be able to identify those parts. Okay. All right. The last, really the last part of this, right, is the reducing and oxidizing agent. Okay. The agent is what's causing the thing to occur in the other part. Okay. Because oftentimes when we talk about oxidation and reduction, usually we're talking about the agent that's causing the change. Okay. So for example, if I have an iron rail out front, right, and it's rusting, okay, what's causing it to rust is the oxygen. Okay. So oxygen is what we would call an oxidizing agent. It causes things to undergo reduction. right? It causes a change to occur. The iron's not doing anything. The iron's just sitting there. So in most of these reactions, there's usually one thing that's causing the reaction to occur, okay? And so usually the thing that's causing the reaction is usually what we focus on. So the agent that is causing the change to occur, okay? So yes, you have both in the reaction. There, you'll see in a second, you have oxidation and you have reduction, okay? It's just like acid base, okay? You have to have both in order for this to work. So if you have something that's causing the change in the other thing, it's like the equal and opposite reaction kind of thing. So obviously we're going to have two agents, but really one of them is what we want to focus on, okay? So the easy way to know this is whatever species is undergoing oxidation, okay, it is the reverse agent. Okay, whatever species is undergoing reduction, it is the reverse agent. Okay, so let's look at this one. Sodium and chlorine, okay, are both 0 to start with. Sodium is losing an electron, undergoing oxidation. Chlorine is gaining an electron, undergoing reduction. So sodium is the reducing agent. Chlorine is the oxidizing agent, okay? Chlorine is causing oxidation to occur, okay? It is causing oxidation to occur in the other species, all right? So that's what the agent definition is really looking at, okay? So once you identify what the action is being taken by a particular molecule, it is causing the reverse. It is causing the opposite to occur in the other thing, okay? All right, so in this particular problem, everything's pretty straightforward. The charges are the oxidation states, okay? So 3 out of the 4 have charges on them, so they're pretty easy. Calcium is a 0, okay? So the calcium is going from a 0 to a +2. The tin is going from a +4 to a +2. So here it's losing electrons, okay? Calcium is losing electrons and is being oxidized, okay? Loss of electrons is oxidation. The tin here is gaining electrons and is undergoing reduction. So its charge is going down, so it's gaining negatives, right? So if calcium is being oxidized, it is causing reduction to occur. It is the reducing agent. The tin 4+ is the oxidizing agent. It is causing that process to occur in the other thing. Okay, so these are the three kinds of questions, 3 things you should be able to identify in a problem, okay? What is the oxidation state of any given molecule, okay? What's happening to that given molecule? Is it undergoing oxidation? Is it undergoing reduction? What is the reducing agent? What is the oxidizing agent? Okay. All right. So like I said, so those 3 things are really what you want to be able to do. Again, some of this should have been kind of refreshed, or we should have recognized at least some of this from the nomenclature stuff. Okay. Let's see. That's pretty much this chapter. Okay, so this chapter has balancing equations, there's stoichiometry, acid-base reactions, precipitation reactions, oxidation reduction. Okay, good question. Why does it go from 0 to if it's well, no, I think it was. Let's go back to this. Talking about the last problem, right? So yeah, so it's losing negative charges, right? If I have 10 electrons, right? So if you think back like to our when we were looking at the stuff before, like if I have 10 protons and 10 electrons. If I lose an electron, you become positive, right? If I lose a second electron, you become +2, right? So it's losing those negative charges, and so the positive nucleus is now unbalanced. That's where all the positive charges are. The negative charges are over here. If it's losing the negative charges, then remember the tug of war is now winning by the center. Okay. It's like, it's kind of one of those times where I should have worn my shirt. It's to get the joke chemistry shirt of the two atoms, and one of them's like, I lost an electron. The other one's like, are you positive? So it's they're losing negative charges and becoming positive. Okay. Okay. All right. I think that's about it for tonight. Like I said, I will have, let's stop.